In the last lecture, we found out the path difference of the first two reflected rays. The light which was incident on the thin film, it got reflected as well as it got refracted, and some of the portion of the light was transmitted and some of the portion is reflected from the thin film. So we found the first two reflected rays from the thin film, they had a path difference of 2 mu t cos r minus lambda by 2. So this is the path difference between the first two reflected rays which are reflected from the thin film. Now the second and third reflected ray. What is the optical path difference between the second and third reflected ray? As we have seen in the first case, at a point capital A, the AC ray and the ray which was refracted and got reflected and then transmitted. So these two rays, they had a path difference which was given by this formula, and this lambda by 2 factor, it was added to this expression because the light which was reflected, the first reflected ray which was reflected from a denser medium, because we are considering the film to have the refractive index which is greater than its surroundings. So the ray which was reflected, the AC ray, it is getting reflected from a denser medium, and hence a path difference of lambda by 2 is introduced in this AC ray, and from there we got this expression minus lambda by 2. Whereas the second ray, A prime C prime ray, you can see the ray after refraction, it gets reflected from a rarer medium. Here is the rarer medium. So there is no path difference lambda by 2 introduced in the A prime C prime ray. Whereas if you see the case of the second and the third reflected ray, earlier we found out the optical path difference between AC ray and A prime C prime. Now let us find the optical path difference between the second and the third reflected ray. You can clearly see the first A prime C prime ray, it is never getting reflected from a denser medium, and similarly this A double prime C double prime ray, it is also not getting reflected from a denser medium. They both are getting reflected from the rarer medium, and hence there will be no path difference introduced. So the path difference between these second and the third ray, it will remain just 2 mu t cos r. The path difference between the second and the third ray, it will be 2 mu t cos r, whereas the path difference between the first and the second ray, it is equal to 2 mu t cos r minus lambda by 2, and this is introduced because of the first ray which is getting reflected from a denser medium, whereas all other rays, they are not getting reflected from a denser medium, and hence the path difference between second and third ray, then third and fourth ray, fourth and fifth ray. So all these rays, the path difference between the two consecutive rays will be just 2 mu t cos r, whereas the path difference between the first two reflected rays will be 2 mu t cos r minus lambda by 2. So this is the main difference. So if the first two rays, they are interfering constructively, if the first two rays, they interfere constructively, means 2 mu t cos r minus lambda by 2 is equal to n lambda, and from there we get 2 mu t cos r is equal to n plus half lambda. So you can clearly see the first two rays, they are interfering constructively, so their path difference, this whole expression will be equal to n lambda, whereas the second and third ray, the path difference between them is just 2 mu t cos r, and by simplifying the first expression, that is 2 mu t cos r minus lambda by 2 is equal to n lambda. So from there we can find 2 mu t cos r, and from there 2 mu t cos r will be just equal to n plus half lambda, which means if the first two reflected rays are interfering constructively, then second and third reflected rays, they will interfere destructively. You can find by putting, or you can equate this whole expression, which is the path difference between first two reflected rays. You can equate this equal to n lambda. From there you will get 2 mu t cos r will be equal to n plus half lambda, and 2 mu t cos r is the path difference between the second and third reflected ray, and that comes out to be equal to n plus half lambda, which is the condition for destructive interference. Hence second and third ray, then third and fourth ray, fourth and fifth reflected ray, they will interfere destructively. So for maxima, path difference should be equal to n lambda, and for minima, path difference should be equal to n plus half lambda. So if the path difference between the first two reflected ray, that is AC and A prime C prime, is equal to n lambda, so the path difference we know between A prime C prime and A double prime, this second and third ray, we know their path difference is equal to 2 mu t cos r. So if AC and A prime C prime means if first and second rays they interfere constructively, then second and third ray, third and fourth ray, and so on, these all rays will interfere destructively. So if the film is seen from this side, from the left hand side, if we see the film, so the first two reflected rays, they are interfering constructively, and all other reflected rays, they are interfering destructively. And we know the amplitude of the first reflected ray is greater than the amplitude of the second reflected ray, and this amplitude is even greater than the third reflected ray. So the amplitude of all the reflected rays, it keeps on decreasing with every successive reflected ray. So the amplitude of first ray will be greater than the second, and second ray's amplitude will be greater than that of third, and so on. So if the first two rays, they are interfering constructively and all other are interfering destructively, and the amplitude of all other rays is negligible as compared to the amplitude of the first two reflected ray, so the film from the left hand side, it will appear bright because the first two reflected rays, they are interfering constructively. Similar is the case when the first two reflected rays, they interfere destructively, that is 2 mu t cos r minus lambda by 2 is equal to n plus half lambda. So when the first two reflected rays, they will interfere destructively, then all other reflected rays, they will interfere constructively. But since the amplitudes of all other reflected ray is negligible as compared to the first two amplitudes, so the film from the left hand side in that case will appear to be dark because the first two reflected rays, they are interfering destructively, and amplitudes of all other rays which are interfering constructively, that amplitude can be ignored, and the light and the film from the left hand side, it will appear to be dark in that case. So what will be the nature of the film, or what kind of appearance will be from this left hand side? It just depends upon the type of interference between the just first two reflected rays. If these two are interfering constructively, the film will appear to be bright, and if these two rays, they are interfering destructively, the film from this left hand side will appear to be dark. So next is the topic of interference by transmitted light. So till now we have been studying the interference by the reflected light, that is the light which was emitted in the left hand side direction. Now is the interference that will occur between the rays BD and B prime. Similarly, there will be third transmitted ray, that will be B double prime, D double prime. Then will be the fourth transmitted ray. So as the reflected rays are interfering, so the transmitted rays will also interfere with each other. The procedure of the type of interference between the transmitted rays, the procedure is the same. That is, we first of all we find the optical path difference between the two rays, and then we equate that optical path difference to n lambda for maxima, and then we equate it to n plus half lambda for minima. So what is the optical path difference between the first two transmitted rays, that is BD ray and B prime D prime ray? So the procedure is the same. So over here the BD ray and the B prime D prime ray, these are the trans. So the procedure of finding the optical path difference is same. We draw a perpendicular from B prime point on the ray BD, that is we draw a perpendicular, and the ray of, let's say this point is L prime on the ray BD, this is L prime point. So the rays of the path difference between L prime D and B prime D prime will be the same. The difference will be this path and the path which is travelled by B prime D prime ray inside the film, and that path is BA prime and A prime B prime, because the two rays, they are getting splitted at B point. At B point the two rays are getting splitted. This is the first transmitted ray, and the other transmitted ray, it comes after travelling inside the film. So this is the extra path which is travelled by B prime D prime, and the path which is travelled by the ray BD extra, which is, that is BL prime. So the path difference, optical path difference between the first two transmitted rays will be the path which is travelled by B prime D prime inside the film, and inside the film, if we find the path difference, it is mu times the geometrical path. It is equal to mu times the geometrical path. So the optical path which is travelled by B prime D prime ray inside the film will be equal to mu times its geometrical path, and geometrical path is BA prime plus A prime B prime, and minus this path which is travelled by BD, and this distance is travelled by BD ray extra in the air. This is the air, so this is the path which is travelled by the ray BD in the air. So we subtract this path because we are finding the optical path difference, because B prime D prime is travelling this path extra and BD is travelling this path extra. So the optical path difference will be equal to subtraction of the both optical paths which are travelled by individual rays. So first of all we will find BA prime and A prime B prime, and these values, they come out to be the same as we found in the case of interference by reflected light. So you can find it easily. BA prime and A prime B prime, these will be equal to each other, and this will be equal to small t, which is the thickness of the film, divide by cos of R, and R is the angle of refraction. So this comes out to be equal to this expression, and BL prime can also be easily found, and it comes out to be equal to H sin I. The procedure is same. You can look into the previous article to find the expression of these variables. So this path BL prime, it comes out to be equal to 2t sin R by cos R times mu sin R, and this is the value of BL prime, and we know the expression for BA prime and A prime B prime. So you can put all the expression in this equation of optical path difference. So the optical path difference between the rays BD and B prime D prime, it will be just equal to mu times BA prime. BA prime is equal to T by cos R plus A prime B prime, which is also equal to T by cos R. So this will be simply T by cos R plus T by cos R times mu minus BL prime, and BL prime will be equal to 2 mu T sin square R by cos R. So you can simplify it. You can take common, 2 mu T by cos R will be common, and in the bracket it will be just 1 minus sin square R, and 1 minus sin square R is equal to cos square R, and we will have cos R in the denominator. So simply the optical path difference between the first two transmitted rays, it comes out to be equal to 2 mu T cos R. And important point is that in the case of reflected light, first two reflected light, we saw that the first reflected light, it got reflected from a denser medium, therefore there was an a term of minus lambda by 2 in the path difference. Whereas the rays BD and the B prime D prime rays, they are never getting reflected from a denser medium. You can see the ray B prime D prime, it is getting reflected from this point, from B point it is getting reflected, and this is getting reflected from a rarer medium. And similarly at point A prime, this ray is getting reflected from the air medium, which is a rarer medium, and then after that it is getting traveled in the air. So as the reflection takes place from a rarer medium, so no extra path difference is introduced. Now is the type of interference. Now this is the optical path difference between the first two transmitted rays, and the optical path difference between the first two reflected rays was equal to this value 2 mu t cos r minus lambda by 2, whereas the optical path difference between the first two transmitted rays, it comes out to be equal to just 2 mu t cos r. So for maxima 2 mu t cos r for the case of transmitted light. If we want a maxima from the right hand side, if the film is viewed from the right hand side from this point, so for that case 2 mu t cos r, it should be equal to n lambda, and for minima, that is the film from the right hand side, if it is viewed from the right hand side, the film will appear to be dark for the case of minima, and it appears dark when the optical path difference is equal to n plus half lambda. So these are the two conditions for obtaining maxima and minima for the case of transmitted light. So you can see the path difference between the first two reflected light is equal to this expression, that is 2 mu t cos r minus lambda by 2. So when 2 mu t cos r, it comes out to be equal to, when 2 mu t cos r minus lambda by 2, it comes out to be equal to n lambda. This comes out to be equal to n lambda. Then the film from the left hand side, it appears to be bright, because this is the condition for constructive interference. And when you simplify it, that expression, when you simplify it, you will get 2 mu t cos r will be equal to n plus half lambda. So I am repeating over here again that when the first two reflected lights, they are interfering constructively, for that case condition will be 2 mu t cos r minus lambda by 2 will be equal to n lambda. And when you simplify that expression, you will get 2 mu t cos r will be equal to n plus half lambda. So keep in mind, first two reflected rays, we are assuming the first two reflected rays, they are interfering constructively. So in that case 2 mu t cos r will be equal to n plus half lambda. And you can see 2 mu t cos r is equal to n plus half lambda. This is the condition for minima for the transmitted light. And when 2 mu t cos r minus lambda by 2, that is when the first two reflected rays, they interfere destructively, then this will be equal to n plus half lambda, and that will be equal to 2 mu t cos r will be equal to n plus 1 lambda. So that in that case n will take values from 0. So 2 mu t cos r will be equal to n plus 1 lambda, or you can say 2 mu t cos r will be integral multiple of lambda when AC and A prime C prime, the first two reflected rays, they are interfering destructively. 2 mu t cos r will be equal to integral multiple of lambda, and you can see 2 mu t cos r is equal to integral multiple of lambda for the case of maxima for transmitted light. So you can clearly see the main point to explain this thing is that when the reflected light, when the reflected or the first two reflected lights, they are interfering constructively, then in the simultaneously the first two transmitted light, they will interfere destructively, because the condition which we obtain for maxima for first two reflected lights is the same condition for minima for the first two transmitted lights. And similarly, if the first two reflected rays, they interfere destructively, then the first two transmitted lights, they will interfere constructively. So if you shine upon a particular wavelength of light, then let's say the reflected light is interfering constructively and the film from the left hand side, it appears to be bright. So there is only a single wavelength of light, a single lambda of light is shown upon this film, and we are assuming that the light which is reflected from the film is interfering constructively. That is, the film from the left hand side, it appears to be bright. Then simultaneously in the same case, the transmitted light, it will interfere destructively, and the light from the right hand side, and the film from the right hand side, it will appear to be dark. So the interference, they are both complementary for the case of reflected and the transmitted light. If the interference is constructive for the case of reflected light, then the interference will be destructive for the case of transmitted light, and vice versa. So for the case of white light, the white light, we know there are 7 colors, there are 7 types of wavelength that constitute white light. If white light is shown upon this film, so let's say there are some wavelengths, they interfere constructively. The reflected lights from the film, they interfere constructively for particular wavelengths from the white light. Let's say 3 out of 4 wavelengths, because there are total 7 wavelengths of light. In general, if we talk about the white light, there are 7 wavelengths. In fact, there are a large number of wavelengths, but we are just in a crude form, we are explaining there are 7 types of lights. So there are 7 types of lights. So let's say 3 out of 4 lights, or 3 out of 4 components, they interfere constructively in the reflected side. So that 3 lights, or that 3 components, will interfere destructively for the transmitted light, and the 4 components, the other remaining 4 components, that interfere destructively in the reflected light, so that same 4 components will interfere constructively in the transmitted light. So these both are complementary to each other. So those components that will appear from the left hand side, they will not appear from the right hand side, and those components of the light that appear from the transmitted section or transmitted part, they will not appear from the reflected part.